Hello, everyone. Today we're going to talk about the very important topic of power flow, which is one of the most important tools we have at our disposal for power system operation and management. Um, if you recall, there are certain requirements for the operation of the power system at steady state. We talked about the fact that we need to make sure that at any point in time, the total generation equals total load, which we defined as demand plus losses. This is necessary to make sure that the frequency remains stable at 60 hertz. We also saw that for every generator, I'm going to use an index of G for it. For every generator G, the amount of active power and reactive power that is injected into the grid has to be within the acceptable upper bounds and lower bounds. So PG is going to be between PG min and PG max, and likewise Q of G, the amount of reactive power injected by that generator into the grid would have to be between the min and max value. We also have a constraint on voltages. So for every node K, I'm going to be using the index of K for nodes and index of G for generators. So for every node K, VK has to be between V min and V max. You notice that here, I don't refer to them necessarily as VK min and VK max because typically the minimum and maximum permissible voltages are uniform across the grid, unlike the upper and lower bound thresholds for active and reactive powers. And then, of course, we want to make sure that no component is overloaded. So none of the series elements like uh, you know, transmission lines, transformers, none of them carry active power, reactive power, or apparent power, which would be above its capacity. These are the requirements that we have to ensure that are maintained at steady state. What does that mean? What that means is we have to be able to assess the amount of active and reactive power that is injected at every node of the system by the generators, the amount of active and reactive power that is flowing through every line or every other series element, like a transformer, for example, across the entire system. And we have to find the voltage magnitudes. This requires a tool, a computational tool, that will give us those values given the parameters of the system, given the network model and the values of the impedances and admittances that are for different lines. That tool is power flow, which is also known as load flow. So different resources you might hear either power flow or load flow. Both of them are the same thing. Today we're going to talk about not necessarily how to solve the power flow problem, but we're going to talk about the fundamentals. So how the equations are derived, and then later on we'll see in future lectures how we actually go about solving those equations. So let's start the discussion by looking at the important concept of admittance matrix. Imagine I have a system in which I have n buses. So that's the total number of buses. I can find a mathematical relationship between the voltages that I have at different nodes and the currents that are being injected into each node. That relationship is going to be through the admittance matrix. So if I look at the vector of currents that are being injected into different nodes, so this is going to be an n by 1 vector, one value for each node. This is going to be a matrix, a square matrix, which is n by n, known as the admittance matrix, times the vector of voltages. I have n buses, so n voltages, hence it's a n by 1 vector. Notice again here, I'm using tilde on top of current and voltage in order to remind myself that these are phasors. Now, the admittance matrix, or the elements of the admittance matrix rather, they're defined as follows. The diagonal elements, let's look at them as YKK. This is going to be sum of all the admittances that are connected to bus K. I have to clarify some very important notation that I'm using here. Every time that I'm using lowercase y here, I'm referring to the actual admittance. So lowercase yki is the actual admittance connected between bus K and bus I. Whenever I'm using capital letter Y, that's indicative of the entry of the admittance matrix. So YKK is the entry in row K and column K of the admittance matrix, but would be the sum of the actual admittances, lowercase y's, that are connected to bus K. What about the off-diagonal elements? The off-diagonal elements, let's show them as YKJ. These are going to be minus the actual admittance that are connected to that node. And you already know this, but just as a reminder, the admittance is going to be the inverse of impedance. So whatever impedance you have connected between different nodes or connected to one particular node, the inverse of that impedance is going to be the corresponding admittance value. All right, the best thing to do right now is to look at an example. So let's imagine I have a three-bus system. In bus one, I have a generator. Let's say bus two has a generator two, and bus three has both a load connected to it as well as, let's say, a capacitor bank. And then these buses are connected to one another through uh, three transmission lines. And let's assume that this line has an admittance of minus J10, this one has an admittance of minus J8, and this one has minus J12. Of course, I'm here clarifying that these are the admittance values. I didn't really have to do that because the moment you say negative and J, you have to realize that this is an admittance, not an impedance. Why? Because let's say I'm ignoring the resistances, the series impedance of that line is going to be JX, but obviously if I convert it to admittance, it's going to be 1 over the impedance, which is 1 over Jx, and you remember that 1 over J is basically minus J. So when you see for these elements, you see minus J, that basically indicates an admittance. And let's say the admittance of this guy, which is a capacitor bank, is J 0.25. And all these values, let's say they are in per unit. All right, let's try to find the admittance matrix. So this is a three-bus system, hence the admittance matrix is going to be 3 by 3. Let's check our definition. I'm going to start with Y11. So the entry in row 1 and column 1. That would be the sum of all the admittances connected to bus 1, which would be a negative J10 and a negative J12, hence negative J22. Y12, so let me provide at least one example here. Y12 by definition is minus the admittance, the actual admittance connected between those two buses. So the actual admittance is minus J10. Negative of that would be J10. What about Y3? Negative of the admittance connected between buses 1 and 3, which is J12. For bus 2, capital Y12 would be the negative of the admittance connected between those buses, which is J10. Y22 would be the sum of admittances connected to that bus, a negative J10 and a negative J8, so negative J18. And then Y23 would be minus the admittance connected between buses 2 and 3, which in this case would be J8. Let's finish the third row as well. Y31, entry in row 3 in column 1, would be the negative of the admittance connected between buses 1 and 3, which is J12. Y32 will be J8. And Y33 would be the sum of admittances connected to bus 3. Notice I have a negative J12, I have a negative J8, and I have a positive J.25. So that would be negative J 19.75. Notice a couple of things here, that this is a three-bus system, and the admittance matrix is a square matrix, 3 by 3. Also notice that it is symmetric. So element 1, 2 is the same as 2, 1. Element 1, 3 is the same as 3, 1. And element 2, 3, and 3, 2 are the same as well. So this is how we find the admittance matrix. And we're going to come back to it later on when we want to derive these equations for solving the power flow. All right, let's move on and talk about the next step for kind of preparing ourselves for solving the power flow equations, and that would be finding the power equation. What I'm going to do is I'm going to assume that I have a bus K, and let's say there is a generator connected to this bus, and that generator is going to be injecting a complex power. Let me show it as SK and G for generation, and I'm going to put the tilde on top to remind myself that this is a complex quantity. And let's say there is a load connected to that bus as well. And again, what I'm going to do is I'm going to assume that the demand at that node, the complex power associated with it is going to be SK, and I'm going to put a superscript of D to indicate that this is demand. And then I could be a bunch of stuff connected to this node. For example, I could have an admittance connected to it. This admittance could represent some constant impedance load, for example. It could represent a capacitor bank. It could represent a reactor bank. In any case, it's something whose impedance or whose admittance would be constant. What I will do is I'm going to use the notation here of YK. Notice again, lowercase y to indicate the actual admittance. And let's say I have another node, another bus that is connected to this bus K through a transmission line, and I'm going to use a pi model for that line. So I have the series elements and I have the two shunt elements. For this series element, I obviously remember that I have a series resistance and a series reactance, which gives me a series impedance. Inverse of that is going to be the series admittance. I'm going to use the notion of YKJ. So the series admittance connecting bus K to bus J. And then for the shunt elements, you know that these are typically equal. But in order to help with my notation here, I'm going to show this as YS, S for shunt, KJ, and then for this guy, I'm going to show it as YSJK. Again, they are, for the most part, going to be equal, but I just want to do this to help me with my notations later. Now, the generator and the constant power load that I'm showing on the left side of this diagram, these are going to have some nonlinear characteristics associated with them. I don't want those nonlinearities to enter my power flow equation. So what I'm going to do is I'm going to combine them together into one variable known as SK tilde. This is the net power injected into bus K, which is essentially defined as the generation at that bus minus the demand at that bus. Notice how generation has the positive sign. Anything that is injected to that node is positive. Anything that is consumed at that node or withdrawn from that node would have a negative sign. So SK would be the net power injected at bus K. What I'm going to do next is I'm going to try to find an equation for SK based on the voltages and the parameters of this network. You remember that the most basic equation for how we have for complex power, SK, would be the voltage at that node times the net current injection at that node conjugate. Now, I do know what the voltage phasor is. I don't know what the current phasor is. However, knowing the voltages and admittances, I should be able to find the current phasor too. So let's try to expand it here. SK tilde complex is going to be VK, I'm going to put it here, times all the currents. What are those currents? I'm going to have a current that flows through this branch. I'm going to have a current that flows through this branch, and I'm going to have a current that flows through this branch. Obviously, if I know the voltages, I can find those currents very easily. So the first current, the one that goes through YK, is going to be obviously the admittance, YK, times that voltage. So voltage times admittance is going to be the current. What about for the second term? So the current that goes through Y SKJ, same thing. It's going to be Y SKJ times VK. What about the component that flows through the series element of the line? This obviously is going to be the admittance, YKJ, KJ, times VK minus VJ. So the voltage at bus K minus the voltage at bus J. In this example, I'm showing just one line that is connected to bus K. In reality, though, I could have a lot of different lines that are connected to it. I can have multiple nodes connected to bus K, to node K. So in the most general sense, this, in fact, might be a summation, which says, hey, J goes from 1 to N, but just keep in mind that J is different from K. It cannot be connected to itself. This is going to be my equation for the current, and obviously there's going to be a conjugate for the whole thing. So now what I see here is I have a bunch of terms within the parentheses that are related to VK, and then a series of terms that are related to VJs over that summation. What I'll try to do next is I'll try to separate these terms. So I will write this as follows. I will say, hey, SK tilde is going to be the VK that I have times, let's look at the term within the parentheses and basically take everything that is multiplied by VK. So that's going to be my YK, which is multiplied by VK, plus I have a bunch of them under the summation. So J from 1 to N, and J is not equal to K, of Y SKJ plus YKJ, right? Of course, the whole thing has a conjugate, and it is multiplied by VK as well, again with a conjugate. Then I will have these terms that have VJ in it. So what I'm going to do is I'm going to expand this and say this is plus, again, VK, times, let's say what I have. What I have here is summation J from 1 to N. J is not equal to K. And what do I have? Y, Kj uh, times Vj. And the whole thing is conjugate. And what I forgot to show here is there is a minus YKJ because I have a negative sign here. So let me put this in parentheses here. Minus YKJ. Now, this may not look like simplification for you, but let's look at the definition. Let's remind ourselves of the definition of the admittance matrix. Let's come back here. We said YKK, the diagonal elements, would be the sum of all the admittances connected to that particular bus. Let's come down here. What do you see? You see the YK. Let me maybe roll this up a little just so you have a better view. So we have YK that is connected to that bus K, plus all these shunt elements and series elements for all the mutual lines that are connected to bus K. So all these guys are included in that term. That essentially means that this term is YKK, the sum of all the admittances connected to bus K. And of course, there's a conjugate too, so I'm going to put the conjugate here too. What else do I have? Let's look at the term on the right. I have negative YKJ. Let's go back to the definition of the admittance matrix. Negative YKJ is essentially the off-diagonal element of the admittance matrix. I'm going to use the capital y again here. So negative YKJ is going to be capital YKJ. Now, what I have is I have a VK here and here. Once it's multiplied by YKK conjugate, VK conjugate, next it's going to be multiplied by YKJ. Again, there's a conjugate here. So YKJ conjugate and VJ conjugate, assuming that J is not equal to K. If I combine this term with this term, I basically get a short form for it, which would be S tilde at bus K, the net power, complex power injected into bus K, which in fact has two terms, the real part and the imaginary part. That is going to be Vk times the summation y kj conjugate vj conjugate when j goes from 1 to n, but notice that I do not put j is not equal to k anymore because essentially I'm combining this summation with this term. Now j can go all the way from 1 to n, so I can have a term associated with ykk and vk as well. This is one of the most important equations that you will see in power flow, and it's something that I'd like you to kind of practice a little bit with and make sure that you can derive it using the basic power equation that we have, this important equation, SK equals voltage times the current conjugate. So that will give us this particular equation. Now, let's look at a particular node K. What are the things that we don't know about node K? We don't know what the active power injection at that node is. We don't know what the reactive power injection is. These are two of the important variables. We also want to know what the voltage magnitude is and what the phase angle is. Remember that when I show this as Vk tilde, it's going to be the magnitude and phase angle, or you can show it in an exponential fashion, V of k, e to the power of j delta k. So I have four variables corresponding to every bus k. These are generally unknown. How many equations do I have? As you can see, for bus K, I can write one equation for complex power. The good news for us, though, this is a complex equation, which means it has a real part and an imaginary part. So while I do have four unknowns, I only have two equations. You obviously remember that if I want to be able to solve a system of equations, I should have the same number of equations as unknowns. If I have five equations, if I have five unknowns, I need five equations. If I have four unknowns and only two equations, I'm not going to be able to solve that system. What should I do then? In solving power flow, we say every bus has four unknowns, four variables, but only two equations. So that means we have 2 degrees of freedom. That means we can choose two of those variables, and then the other two that are going to be unknown can be found using the two equations that we can solve, we can write for that node. Depending on which ones of those two variables are unknown, we can have different types of buses. These are known as slack bus, PV bus, and PQ bus. First, slack bus. This is also known as reference bus. So in slack bus or reference bus, what we assume is that Vk and delta K are known. We know what voltage magnitude we have. We know what voltage phase angle we have, but Pk and Qk are unknown. In power flow, we typically assume that we only have one slack bus or one reference bus. There are some exceptions that we're not going to talk about it in this class. So for the purpose of our discussion here, we will only have one slack or one reference bus. And this is typically a large power plant that has the capacity to inject as much active power and as much reactive power as you need, and is going to be able to supply all the losses in the system as well. For a slack bus, we typically assume that the voltage magnitude is 1 and the phase angle is 0 degrees. The phase angle of the slack bus typically acts as the reference for every other phase angle. So every other voltage phase angle in the system is going to be compared with the a slack bus phase angle, which is 0. The second type of bus that we have is PV bus. A PV bus, as the name says it, is a bus in which active power and voltage magnitude are known. So P and V are known, but then reactive power at that bus and phase angle of the voltage are unknown. Notice in each of these cases, I have two known variables and two unknown variables. Then those two unknown variables are going to be solved using the two equations that I have for that bus. This way I can make sure that I would have the same number of equations as unknowns. Now, a bus that can regulate the active power and the voltage magnitude is essentially a generator bus. So typically, one of the buses that has the largest generator would be considered to be the slack bus, and everybody else is going to be a PV bus. Generators can regulate the voltage magnitude at their terminals using the excitation system and can also regulate the amount of active power injected into the system using the governor system. So both P and V can be controlled, and then Q and delta are the unknowns that can be solved using power flow. And then the last one, the third category, would be PQ bus. A PQ bus is going to be a bus for which active power, P of K, and reactive power are known, but then voltage magnitude and voltage phase angle are unknown. A PQ bus is a bus for which we don't know anything about the voltages, but we know how much power is being injected, or better said, consumed at that node. So these are load buses. So typically, the largest power plant, the largest generator bus that we have in the system is going to be considered as the slack bus or the reference bus. Every other generator bus is going to be PV bus, and every load bus is going to be PQ bus. Pay attention here that now for each of these buses, we only have two unknowns, or I should say two unknowns, and then we have two equations for them. So we're going to have the same number of equations as unknowns, hence we can solve this system. Now, before we finish this discussion, I want to tell you about the numbering convention that I typically use in PowerFlow. You don't necessarily have to do that, but it kind of makes things a little bit easier. Usually, in order to number buses, we assign bus number 1 to be the slack bus, and then the next buses are going to be PV buses. The rest of them towards the end are going to be the PQ buses. So let's say I have a system with n buses. So they start from 1, 2, 3, and they go all the way to n. What I will do is I will consider bus number 1 to be the slack bus. So I name that bus number 1. The rest of them, the rest of the PV buses, generator buses, are going to be buses 2, 3, 4, and so on. And then whatever remains is going to be my PQ buses. Let's remind ourselves quickly of what we talked about today. First, PowerFlow is an important tool that we have in order to help us verify that no generator is providing more active or reactive power than it can, that no component is overloaded, that no node voltage exceeds the upper bound or the lower bound. These constraints that we have for operation of the power system at steady state. We talked about forming the admittance matrix. Remember that the admittance matrix is a square matrix. If you have n buses in the system, the admittance matrix is going to be n by n. It has diagonal elements, which are defined as the sum of admittances connected to that bus, and then off-diagonal elements, which would be the negative of the admittance connected between those two buses. And then we talked about the very, very important equation, power equation for a node. This is kind of the one that I would really like you to remember, and that the net power injected into bus K, which consists of the active power and reactive power, can be found using the node voltages in the system, as well as the elements of the admittance matrix. And lastly, we remember that for every node, we have four unknowns, four variables, which are the active power, reactive power, voltage, magnitude, and phase angle, but only two equations. In order for us to be able to solve the system of all these equations across the system, we have to have the same number of equations as unknowns, which means for different nodes, different buses, we have to assume two of these values out of the four variables, out of the four unknowns. Two of them are known, are given to us. This gives us three types of buses: slack bus, for which the voltage magnitude and phase angle are known, PQ are known, PQ are unknown. PV buses, that are the remaining generator buses, for which I know P, I know V, I do not know Q or delta. And then PQ buses that are load buses, P and Q are known, V and delta are not known. We're going to stop here for today, and hopefully in the next class, we're going to start talking about how we will be solving these series of nonlinear equations in power flow.